Hi students, it's Mr. Bornheimer, and this is the first part, or we'll call it section A, of our Unit 3 study on acceleration in physics. So students, this is section A. The concept here is acceleration. Okay, the big idea is that acceleration is a rate of change in an object's velocity. Now, that is so critically important that you look at it as a rate of change in velocity. Velocity already is a rate. So we're going to start thinking about some of those ideas, in this presentation. Now, we're going to be using motion diagrams, and we're going to be asking ourselves, what is this concept called acceleration? How is it different from velocity? And what information can you learn from a velocity time graph? Now, we've already talked about position or displacement time graphs, but we haven't really discussed velocity time graphs so much in depth. So we're going to take a look at that in more detail. Okay, we're going to need to really know what a vector is. And some of our new vocabulary will be acceleration, velocity time graph, average acceleration, just like average velocity, and instantaneous acceleration, very similar to instantaneous velocity. However, in saying that, they are not the same. But you'll see this concept of average and instantaneous coming back again and again. All right, now this idea of uniform motion is really important, okay? Anything that moves at a constant rate of velocity is considered to be in uniform motion. So if you're on a moving sidewalk in an airport, you're in uniform motion. Very few objects actually move with uniform motion in nature. Almost everything is speeding up or slowing down or changing direction in some way. Okay, so some examples of non-uniform motion, as you can be seen here, would be like speeding up, applying the brakes, falling objects. If you've ever seen the hammer throw or like the discus, or even like a merry-go-round that's speeding up, that would be along a circular path. And the non-uniform motion that would be like thrown or projectile might be like a baseball or a football, Hail Mary kind of thing. All right, so you can feel the difference between uniform and non-uniform motion. When you move in non-uniform motion, you actually feel pushed or pulled. So like if your car makes a sharp turn and you feel yourself kind of going into the door, or if you're on a merry-go-round and you feel like you're going to fly off, or you're on a roller coaster and you feel like you're going to fly out, those would all be considered non-uniform motion. However, when you are in uniform motion, in constant motion, there's no change in direction, there's no change in speed, then if you were to close your eyes, you wouldn't feel a thing. A good example of this would be an elevator. Let's say an elevator starts up and then hits a constant rate. It's going up at a constant rate. Okay? As long as the elevator is moving at a constant rate and you have no reference to the outside world, if you were to close your eyes, there would be no physical way for you to tell that you were moving. There would be no way. Okay? Just a little bit of a video here, just to kind of show you. Okay, here's non-uniform motion, and here would be an example of uniform motion. So you can see, go ahead, and non-uniform would be like on a roller coaster, twists and turns, up and down, changes in speed. Uniform motion would be a constant speed and a constant direction, so moving up at one direction at a constant rate. That would be uniform motion. Okay. Now, motion diagrams are going to come into play here. They are important. We see in these four motion diagrams are the four very typical examples of what you might see in motion of an object. You have two constant motions, or two constant ones. You have a person that is motionless, so a constant velocity of 0. And then you have a person here that's moving at a constant rate, so a constant speed, constant direction. Okay, and so we'd say they have constant velocity. However, you do have two that have changing velocities. You have one where an object is, or a person is, speeding up. And we know they're speeding up because we know that the distance between the persons is the same time. However, their actual distance or position in meters, per se, is increasing. In the slowing down example, we see this distance here is large, and then it gets smaller, and then it gets smaller, and then it gets smaller. So we see, again, a changing displacement for each time interval. Okay, that would be slowing down. Notice that when we talked about acceleration at the very beginning, the big idea was that it's a change in an object's velocity over time. So in the first two, A and B, we see no change in velocity. Person A is motionless and they stay motionless. In part B, the person is moving at a constant rate and they continue to move at a constant rate. However, in C and D, we see a person speeding up, so velocity increasing. We see a person slowing down, velocity decreasing. Now, there are two major indicators of a change in velocity. The major indicators would be this space between these, okay, individuals increasing. The lengths of the velocity vectors getting longer or the lengths of the velocity vectors getting shorter. Okay, so you can see this is kind of just a breakdown on objects speeding up, and here's a breakdown on objects slowing down. And we can see both of them here again. All right, the formal definition of acceleration, okay, is the rate at which an object's velocity changes. Now, when we're talking about a rate, we're talking a change in velocity, and rates always deal with time. So it must be a change in an object's velocity per time or per time interval. Okay? When we say that an object's velocity is changing at a constant rate, so going from 1 meter per second to 2 meters per second to 3 meters per second, increasing each time by a meter per second, that would be a constant increase. Or we could say it's going from 5 meters per second to 4 meters per second to 3 meters per second to 2 meters per second to 1 meter per second, talking about decreasing at a constant rate. That would be called acceleration, where the velocity is changing at a constant rate per unit of time. Okay. So if we were to go ahead and analyze this from a vector standpoint, and this is important for us because as we look at vectors, it becomes crucial that we can take them and we can do vector diagrams, tail to tip, talking about how we would actually formally define this idea of acceleration using vectors. So if we take a look at this, we see that this is an example of an object that's increasing its velocity. It's a changing velocity. We see that it starts over here on the left and it's going slow, and then it's speeding up, then it's speeding up some more, then it's speeding up, then it's speeding up, and then there's a very large vector over here that shows an even greater increase in velocity. Now we really could look at any two vectors on this in this particle or motion diagram. However, we're just going to isolate these two central ones. Okay? Now acceleration is a change in an object's velocity. When we talk about a change in an object's velocity, we're actually talking about, okay, we're actually talking about this idea where if you have a change in velocity, it's actually equal to the final velocity minus the initial velocity. We've seen this same sort of thing time and time again when we looked at displacement, where we looked at df, so final position minus initial position, or delta t, delta time, where we looked at tf minus ti. So we see change in position, change in time. Well, change in velocity is really no different. It's vf minus vi. So if we were to actually apply that to the vectors vf and vi, we would see that we have vf and then we would subtract vi. Now it leaves a very small, what we call resultant vector right here. That's called a resultant vector. And what that is that represents the change in velocity. It will always have the same direction as the larger vector. And because a change in velocity is proportional to the change in to our acceleration per time interval, if we look at this per unit time, that equals acceleration. And this concept of acceleration can be applied here when we see that, hey, the object's accelerating because there's an increase in the velocity, and this is that change in the velocity per that unit time. Okay, and you can kind of see this all broken down in the text here. All right, now, direction of acceleration, okay, you need to know this. And the reason is that the direction of acceleration will determine whether an object is speeding up or slowing down. Okay? The idea here is if the acceleration of the object is in the same direction as the velocity. So same direction as the velocity. So let's say an object is accelerating in this direction, and the object's velocity is also in that direction. So it's moving in this direction, then the speed will increase. Okay? Now this direction could be positive or negative. The direction, positive or negative, doesn't matter. What matters is that the acceleration and the velocity are in the same direction. I don't think I can specify that enough. Same direction. However, if the acceleration is in the opposite direction to the velocity, then this represents a situation where the object is slowing down. So an opposite direction, so if they are going against each other, then the speed decreases. So they are actually going to show a slowing down motion. All right, so this acceleration and velocity, if they're in the same direction, whether they're both be going positive or they're both going in the negative direction, doesn't matter. If the acceleration is in the direction of the velocity, the object will speed up. If, however, the velocity is going against the acceleration, then the object will slow down. A great example of this would be gravity. Let's say that gravity is always pulling us towards the Earth. So let's say here's the Earth, and we'll call the Earth negative. As objects fall towards the Earth, they're moving in the negative direction. Okay? We would say that gravity has an acceleration in the downward direction. Now, if you throw an object upwards, okay, so let's say it has an upwards velocity, you can see that the acceleration due to gravity, okay, is downward, velocity is upward. So in theory, based on what we just talked about, any object moving away from the Earth will, in theory, slow down. Now you can test this. Take a basketball, baseball, whatever, and just toss it up in the air. If this is true, the object will slow down and eventually return to you. If, however, it's not true, then the object should speed up and leave our atmosphere. I think you can probably guess what's going to happen. Now, if an object is falling towards the Earth, so let's say the velocity is in the same direction as the acceleration, then in theory, based on this and what we just talked about, it should speed up. So let's think about that. You toss an object up, it comes to a brief stop, it starts to fall back down. Is it speeding up or is it slowing down? We know that objects that are falling tend to speed up. Okay, that's why it's so dangerous to fall from such high heights, like a building or a bridge or whatever, because we get faster as we approach the ground. So we see this concept of acceleration and velocity acting in the same direction up here and in different directions down here. And the direction will make a very important difference, and it's a great distinction that we're going to need to make when analyzing motion and different systems and their different values. Okay, here's a great chart that we're going to kind of look at ending with here. You have acceleration and velocity in the same direction here. So if they're in the same direction, regardless of direction, positive or negative, they should be speeding up. Now we see that the velocity vector here is getting longer and longer and longer. So we see that it is indeed speeding up. Okay, so that is happening. Here we see that they're in opposite directions. So we can automatically say that they're slowing down. Doesn't matter what direction they're going, positive or negative. If these are opposite, it's going to slow down. So we take a look. Velocity is great, and it's getting less and less and less. So yeah, this is slowing down. All right, now we see that acceleration and velocity are in the same direction again. Doesn't matter what direction, as long as they're the same direction. So we should see this speeding up, and it looks like they're pointed to the left, so we should see it speeding up to the left. So we look at this and we say, okay, it's small, and then it's getting larger and larger and larger. Okay, so it is speeding up. So that's true. And down here we see that, hey, they're in opposite directions again. Okay, so this time we're going to say, okay, the object always moves in the direction of its velocity, so it's going to be moving to the left. And because they're in opposite directions, it's going to be slowing down. So we say, okay, it starts on the right, and it's getting slower and slower and slower. So yeah, it's slowing down. and it's moving to the left. This is how we use acceleration and velocity when we're looking at objects and their motion. And we'll talk more about this and break this down in greater depth later. This ends our unit, not our unit, but our section A, part of unit 3, where we're looking at acceleration in physics. Okay, thank you for watching, and have a great day.